Picture the Milky Way exactly as you have always imagined it. A flat, spiral disk of F-stars, roughly 100,000 light-years across and about 1,000 light-years thick. A glowing pinwheel of suns suspended in the dark. You have seen the photographs. You know the shape. You believe, with the quiet confidence of someone who has seen the poster on enough classroom walls, that you understand the basic architecture of the place you call home. Now forget it, all of it, because what actually surrounds the Milky Way above and below its glowing disk is not darkness, it is not emptiness, it is not nothing. It is a structure so vast, so layered with competing mysteries, and so fundamentally strange that when astronomers finally began to map it properly in the last decade, many of them reported the same first reaction: disbelief. Not academic skepticism, but the raw, chest-tightening disbelief of a person who has just realised that the house they have lived in their entire life has wings they never once suspected. There are bubbles of hot gas 2 million degrees Fahrenheit erupting above and below the galactic centre, stretching 50,000 light-years in each direction, and nobody can agree on what made them. There is a ghost galaxy, the skeleton of an ancient collision, whose bones lace the entire surrounding sky in a web of stolen stars, and we have only just begun to read the full inscription. There is a halo of invisible matter so massive that if it were visible to the naked eye, it would occupy a quarter of the entire night sky from where you stand. And the question of what actually lives in all of that space, above and below the plane where we exist, is one of the most consequential open problems in all of modern science. So, what is actually up there? Let us begin, as all good stories do, with the lie we were told in good faith. For most of the history of human civilization, the Milky Way was simply the sky. It was the river of light that the ancient Greeks called Galaxias Kyklos, the Milky Circle, visible on every dark night from every unlit hillside on Earth. Before the age of electric light, before the smog of industry, before the orange glow of cities swallowed the countryside, anyone who walked outside and looked up could see it. A diffuse, softly luminous band arching from horizon to horizon, denser in one direction than another, brighter near the constellation Sagittarius, where the galactic centre lies 26,000 light-years away. Philosophers and poets gave it myths. Navigators used it as a compass, but nobody, until the early 20th century, truly understood what it was. The realization came in stages, and each stage was a humiliation for the human sense of scale. In 1610, Galileo turned his rudimentary telescope toward that soft river of light and discovered it was made of individual stars, thousands upon thousands of them, packed so tightly together that the naked eye could not resolve them individually. The Milky Way was not a cloud or a stain on the celestial sphere. It was a vast collection of suns. That was the first recalibration. The second came in the 1920s, when astronomer Harlow Shapley at the Mount Wilson Observatory in California used a class of pulsating stars called Cepheid variables, whose luminosity varies with clock-like periodicity, allowing astronomers to calculate their true brightness, and therefore their distance, to map the positions of globular clusters, the ancient spherical swarms of hundreds of thousands of stars that orbit in the halo above and below the galactic disk. What Shapley found was staggering. The globular clusters were not distributed evenly around the sky. They were concentrated in one direction, towards Sagittarius, which meant we were not at the centre of the Milky Way at all. We were out in the suburban spiral arms, roughly 2/3 of the way from the centre to the edge, orbiting at a speed of approximately 220 kilometers per second around a hub we could not see. We were not the centre of our own galaxy. That second recalibration was, and remains, one of the most quietly devastating conclusions in all of science. Then came the third, and it is the one that underlies everything in this documentary, when astronomers began to seriously study not just the disk of the Milky Way, but the enormous three-dimensional volume surrounding it. They discovered that the disk, the thing we had been drawing in textbooks and pinning on classroom walls for a century, represents a profoundly misleading picture of our galaxy. The disk is, in a very real sense, the thin, luminous skin of something far grander and far stranger. It is the visible minority. A galaxy is not its stars. A galaxy is primarily the dark, diffuse, multi-layered environment that surrounds those stars, extends above and below them in every direction, and shapes their entire existence. The stars are the decoration. Everything else is the architecture. Let us build that architecture layer by layer, because it is only when you understand the full stack of what exists above and below the Milky Way that the real mysteries come into focus. Start at ground level. The thin disk of the Milky Way, the pancake layer of spiral arms, gas clouds, and young blue stars that you see in every photograph, is approximately 100,000 light-years in diameter, and at most locations across its span, no more than about 1,000 light-years thick from top to bottom. To put that in proportion, if the Milky Way were the size of a standard CD disk, the thin disk where almost all the stars reside would be thinner than a human fingernail. The galaxy we think we know is a wafer. It is a film, and it floats inside something enormously larger, directly above and below the thin disk. Before you leave the recognizable galaxy entirely, there is the thick disk. This is a second stellar population, older and less metal-rich than the thin disk stars, with stars that tend to travel on orbits that carry them to greater heights above and below the midplane than thin disk stars do. The thick disk extends roughly 3,000 to 4,000 light-years above and below the galactic plane, considerably more than the thin disk, and it contains stars that formed in the galaxy's turbulent youth between 8 and 12 billion years ago. The thick disk is the Milky Way's scar tissue. It records an era of violent mergers and gravitational upheaval that predates the more orderly, settled galaxy we inhabit today, and in 2022, the Gaia mission revealed that the thick disk is substantially older than previous models had assumed, dating to a period when the young Milky Way was still growing and the universe itself was less than 5 billion years old. Above and below the thick disk, the density of stars drops sharply, but they do not disappear. What you encounter next, extending from a few thousand light-years above the plane to tens of thousands and eventually hundreds of thousands of light-years out, is the stellar halo. The stellar halo is not a disk at all. It is an enormous, roughly spherical, though as we will discover, not perfectly spherical, cloud of ancient metal-poor stars scattered through the space surrounding the galaxy at very low densities. Where the thin disk might contain one star per cubic parsec, the stellar halo at its outermost reaches contains fewer than one star per 10,000 cubic parsecs. It is extraordinarily sparse. It is also extraordinarily ancient. The stars of the outer halo are among the oldest objects in the universe. Some of them formed within the first 2 billion years after the Big Bang. Fossils of a time before the galaxy had its current shape, before the spiral arms had been drawn out, before the sun had been born. The stellar halo extends to distances of at least 300 light-years from the galactic center in every direction, 3 times the diameter of the visible disk, and recent detections of a class of variable stars called RR Lyrae, which pulsate with known luminosities and therefore serve as precise distance markers, have found individual Milky Way halo stars at distances of more than 1 million light-years from Earth. 1 million light-years. The Andromeda Galaxy, our nearest large galactic neighbour, sits about 2.5 million light-years away. The outer stellar halo of the Milky Way extends almost halfway there, but even the stellar halo is not the end of the story, not by an enormous distance. Surrounding the stellar halo, filling the vast volume beyond the last traceable stars, is a multi-layered cocoon of gas, dark matter, and gravitational influence that defines the true boundary of the Milky Way as a gravitational system. This is where the story gets both extraordinary and deeply, productively unsettled, because when astronomers attempt to map what is actually in that space, above and below the plane, out to the farthest reaches where the galaxy's gravity still holds sway, they find not emptiness but a riotous complexity. They find bubbles, fountains, ghost galaxies, ancient scars, and an invisible architecture of matter that we have never directly observed. The question is not whether something is up there. The question is whether we can understand what it is. And here is the first open loop that will run through every chapter of this story. Even after decades of dedicated observations with the most powerful telescopes ever built, we do not know the precise shape, mass, or full extent of the region that surrounds our own galaxy. We live inside a structure we cannot see, cannot fully measure, and cannot fully explain. The Milky Way, in a very literal sense, remains a mystery, and most of the mystery lies directly above and below our heads. There is a number that I think deserves to sit with you for a moment before we continue. The total mass of all the stars in the Milky Way is estimated at roughly 50 billion solar masses. That sounds large, and by any human standard it is incomprehensibly large. But the total gravitational mass of the Milky Way, the mass required to explain the motions of stars in the disk, the orbits of satellite galaxies, the trajectories of globular clusters, the behaviour of the galaxy as a self-contained gravitational system, is somewhere between 1.2 and 1.9 trillion solar masses. The most careful recent analysis, using the positions and velocities of globular clusters as gravitational probes, settles on approximately 1.29 trillion solar masses as the preferred estimate. The stars account for roughly 4% of the total mass, perhaps a little more when you add gas and dust. But the overwhelming majority, something like 90% of everything that the Milky Way gravitationally owns, is invisible. It emits no light. It reflects no light. It absorbs no light. It has never been directly detected by any instrument on Earth or in orbit, and yet it must be there because without it, the galaxy cannot hold itself together. Without it, the stars in the outer disk would fly off into intergalactic space, because the visible mass at the galactic centre provides nowhere near enough gravity to keep them in their orbits at the speeds we observe. This is dark matter, and before we go a single step further into the structure above and below the Milky Way, we have to understand why it is impossible to tell this story honestly without it. Because dark matter does not just contribute to the mass of the galaxy, it is the galaxy's skeleton. The stellar disk, the stellar halo, the gas clouds, the satellite galaxies, all of it floats inside a halo of dark matter that defines the true gravitational boundary of the Milky Way system, and that halo extends far further above and below the disk than any star we have ever catalogued. The dark matter halo of the Milky Way is not a flat disk. It is, as far as we can currently determine, roughly spheroidal, though its precise shape is a matter of ongoing and deeply contested debate. Simulations based on the standard cosmological model, called lambda CDM, predict that dark matter halos should be slightly flattened and possibly triaxial, stretched differently along 3 different axes. Observations suggest it may be oblate, like a slightly squashed sphere, though recent work using the positions of satellite galaxies and tidal streams has proposed it may be significantly tilted relative to the disk of the Milky Way. The dark matter halo does not align neatly with the galaxy's visible structure. It tilts, it leans, and as we will see, that tilt has become one of the most surprising and revealing clues to the Milky Way's entire history. The extent of this halo is staggering. A 2020 study predicted the edge of the Milky Way's dark matter halo at approximately 292 kiloparsecs from the galactic center. That is around 952,000 light-years, or just under 1 million light-years. Other analyses stretch it further, with some simulations suggesting the dark matter distribution associated with the Milky Way could extend to almost 2 million light-years across. To frame that in terms you can feel, the visible disk of the Milky Way, the thing that looks like a galaxy when you see it in a photograph, occupies roughly 5% of the total diameter of the dark matter structure that generates and maintains its gravity. The disk is a campfire at the centre of a continent-wide wilderness. Here is where the mystery begins to compound, because even within the dark matter halo, there is structure, there is gas, there is a layered, dynamic environment that has been actively shaped by the galaxy's entire history, and much of what is happening in that space is still being discovered, sometimes literally within the last 5 years. let us talk about the circumgalactic medium because I think it may be the most underappreciated layer of the galaxy, and the one whose significance is only now beginning to be taken seriously. The circumgalactic medium, the CGM, is the diffuse gaseous halo that fills the space between the edge of the galactic disk and the outer boundary of the dark matter halo. It is not empty space with a little gas drifting through it. At the temperatures measured by X-ray telescopes, it is a hot, turbulent, dynamic medium of ionized plasma, with temperatures reaching several million degrees Kelvin in its hottest phase. It is the medium through which the galaxy breathes. Gas falls in from the larger cosmic environment to fuel star formation. Gas is blown outward by supernova explosions and stellar winds in the disk. Gas cools, condenses, and rains back down onto the disk in what astronomers call the galactic fountain, a continuous cycle of matter rising, cooling, and falling that takes hundreds of millions of years to complete one circuit. The circumgalactic medium is not merely the space above and below the galaxy, it is the galaxy's circulatory system, and its mass is extraordinary. A 2012 study using the Chandra X-ray Observatory found evidence that the hot gas halo enveloping the Milky Way could contain a mass comparable to the mass of all the stars in the disk combined. Perhaps 50 billion solar masses of hot gas, invisible to optical telescopes, detectable only because it emits faint X-rays as its trillion-degree particles slam into each other. This finding was immediately significant not just for what it said about our galaxy, but for what it might say about a long-standing puzzle called the missing baryon problem. The missing baryon problem is one of those quietly devastating cosmological conundrums that does not get enough attention outside technical papers. Here is the issue. The standard cosmological model, built on decades of observations of the early universe, predicts that ordinary baryonic matter, protons, neutrons, electrons, all the stuff that makes up stars, gas, dust, and people, should constitute about 5% of the total energy content of the universe. When cosmologists count up all the baryons they can find in stars and cold gas clouds across the entire observable universe, they account for only about half of that predicted total. The other half is simply missing, absent, unaccounted for. The leading hypothesis, now strongly supported by the Erisita X-ray telescope data from 2024, is that the missing baryons are not actually missing at all. They are hiding in the warm, hot intergalactic medium and circumgalactic medium, the vast, diffuse million-degree plasma that fills the halos of galaxies like our own. They are invisible to optical telescopes. They are faint even to X-ray telescopes, but they are there above and below every galaxy in the universe in a gaseous phase so hot and so diffuse that it took us decades to develop instruments sensitive enough to find it. The Erisita telescope, launched aboard the Russian-German Spectrargy spacecraft on July 13, 2019, and completing its first all-sky survey between December 2019 and June 2020, found that the warm, hot CGM of the Milky Way, at temperatures around 10 million Kelvin, extends to at least 100 kiloparsecs above and below the galactic disk, and contains a mass broadly consistent with the missing baryon estimates. This is a critical finding. It suggests that the answer to one of cosmology's most persistent accounting problems may be literally surrounding us, hanging above our heads and beneath our feet in a vast, invisible sphere of 10 million degree gas that no human eye could ever see, and that required some of the most sophisticated instruments in scientific history to detect. But the Erisita survey revealed something else, something that had been glimpsed before, dimly and incompletely, and that the full sky resolution of Erisita finally made undeniable. Something had punched enormous holes in that halo, two enormous bubbles, rising above and plunging below the galactic disk, symmetrical, enormous, and still unexplained. The Milky Way, it turns out, has been bleeding upward and downward into the sky for millions of years, and the scar tissue of that bleeding may be the most extraordinary structure in our entire galactic neighbourhood. On November 9, 2010, a paper appeared in the Astrophysical Journal authored by a Harvard astronomer named Meng Su, along with Tracy Slatier and Douglas Finkbeiner. The paper's title was Compact and Clinical: Giant Gamma Ray Bubbles from Fermi-Lat, AGN Activity or Bipolar Galactic Wind. The content was anything but clinical. Using data from NASA's Fermi Gamma Ray Space Telescope, Su and his colleagues had identified two enormous lobes of gamma ray emission, erupting above and below the centre of the Milky Way. Each lobe stretched approximately 25,000 light-years outward from the galactic plane, meaning the full extent of the two structures together, measured from the tip of the northern lobe to the tip of the southern, was approximately 50,000 light-years, half the diameter of the visible disk itself. And they were not faint, whisper-thin features that required statistical massaging to extract. They were, once Finkbeiner's group had subtracted the known gamma-ray foreground emission carefully and precisely striking, hard-edged, sharply bounded, like objects blown up from within, rather than diffuse emission bleeding gradually into the sky. The astrophysics community's reaction was, in the most literal sense of that overused phrase, genuinely stunned. Gamma rays at those energies, in that geometry, in that location, emerging from the galactic centre, had simply not been predicted by any leading model of the Milky Way's structure. The structures were not in the textbooks. They were not in the simulations. They had been hiding in data that had been publicly available, staring out of the sky, and nobody had pulled the foreground away carefully enough to see them until Su and his team did. These became known as the Fermi bubbles, and for a decade they occupied an uncomfortable corner of galactic astrophysics, too large to ignore, too mysterious to explain, radiating energy equivalent to what you would get from 100,000 supernova explosions concentrated and directed outward in two symmetric jets. The gas inside them, once spectroscopic measurements became possible, was found to be moving at roughly 3 million kilometers per hour, outward, away from the galactic centre, driven by some enormous past event. 2 to 4 million years ago, the best estimates suggest, something in the galactic centre released a truly colossal quantity of energy, and the aftermath of that release is still propagating outward through the halo today, visible to every gamma-ray telescope with wide enough eyes. But what exactly released that energy? There are two leading candidates, and 15 years after the discovery, neither has been definitively confirmed. The first candidate is a brief episode of extreme activity from Sagittarius A, the supermassive black hole at the centre of the Milky Way. Sagittarius A is, today, one of the most quiescent supermassive black holes known in the local universe. It accretes matter at an almost negligible rate, flickering with modest X-ray flares, but producing no sustained jet, no visible accretion disk, no evidence of the kind of voracious feeding that drives active galactic nuclei in distant galaxies to outshine entire star clusters. But dormancy today does not mean dormancy forever. Several lines of evidence suggest that Sagittarius A was considerably more active in the recent past. ESA's integral satellite found X-ray echoes from molecular clouds near the galactic centre, suggesting that as recently as 350 years ago, the black hole was releasing roughly 1 million times more energy than it does today, and a more sustained burst of activity. A period where infalling gas triggered something approaching a low luminosity AGN event 2 to 4 million years ago is entirely consistent with the energy budget required to inflate the Fermi bubbles. The second candidate is a concentrated starburst in the central molecular zone, the dense ring of star-forming gas surrounding the galactic centre within the innermost few hundred light-years. A period of intense, rapid star formation in this region would have produced an extraordinary number of massive stars in a relatively short time. Those massive stars would have lived fast and died as supernovae in rapid succession, and the combined energy of thousands or tens of thousands of supernovae erupting within a small volume over a few million years is by some calculations sufficient to drive the kind of outflow observed in the Fermi bubbles. The energetics work, the geometry is plausible, and the current conditions in the central molecular zone, where giant molecular clouds are forming stars at anomalously high rates even today, are consistent with this kind of episodic starburst activity. The uncomfortable truth, as of 2024, is that the evidence points toward both processes, and the scientific community's best answer is a deeply unsatisfying, probably some of both, in proportions we haven't determined. As one review in the Proceedings of the National Academy of Sciences put it that year, Fermi bubbles are bursting from our galaxy. Their origins remain a mystery. I find this. The existence of a structure half the size of the visible galaxy, erupting from our own galactic centre, and still unexplained after 15 years of dedicated study, one of the most genuinely arresting facts in modern astronomy. It is not that we lack data. It is that the data refuses to resolve cleanly into a single story. The Fermi bubbles are our galaxy's loudest unsolved mystery, shouting gamma rays into the halo, and we are still learning to speak the language. Then came Erecita, and the mystery went from loud to thunderous, when the Spectra RG satellite completed its first full all-sky X-ray survey in 2020, and the team at the Max Planck Institute for Extraterrestrial Physics in Garching began analysing the data. They found the Fermi bubbles. They expected that. What they did not expect was the size of what they found when they looked at X-ray wavelengths rather than gamma rays. The Erecita bubbles, named for the instrument that first captured their full extent, are considerably larger than the Fermi bubbles. Where the Fermi bubbles extend roughly 25,000 light-years above and below the galactic plane, the Erecita bubbles extend to approximately 50,000 light-years above and below the plane. The total structure, the full hourglass-shaped edifice of hot gas erupting symmetrically from the galactic centre, is comparable in scale to the entire visible disk of the Milky Way. The X-ray temperature at the boundaries of the Erecita bubbles is around 2 million Kelvin, and those boundaries are sharp, not gradually fading edges but distinct shock fronts where the outrushing hot gas has piled up the surrounding circumgalactic medium into a compressed wall. The bubble edges are, in the most precise available terminology, the frozen moments of an ancient explosion caught mid-expansion. The relationship between the Fermi bubbles and the Erecita bubbles is now understood as a nested structure, most likely recording two successive episodes of energetic activity from the galactic centre, separated by some millions of years. The larger Erecita bubbles may record the older, more energetic event, possibly the most powerful sustained outburst Sagittarius A has produced in the past 100 million years. The smaller Fermi bubbles, nested inside the larger X-ray structure, record a more recent event, perhaps 2 to 4 million years ago, that re-energized the inner portions of the already inflated structure. The energy required to create the Erecita bubbles is staggering. The best estimates put it at approximately 1056 ergs, equivalent to the total energy released by 100,000 supernovae detonating in concert. That number sounds abstract until you consider that it is roughly the same energy budget estimated for the most powerful known AGN outbursts in distant galaxies. The Milky Way, apparently serene and suburban in the modern universe, carries the scar tissue of a past eruption that rivals the most violent events observable in the entire observable universe. But here is the complication that no summary of the Fermi and Erecita bubbles can afford to skip, because it is where the story stops being merely dramatic and starts being profoundly important for our understanding of galaxies in general, the galactic fountain. Even in the absence of dramatic eruptions from the galactic centre, the disk of the Milky Way is constantly blowing material upward and downward into the halo above and below it. Every time a massive star ends its life in a supernova explosion in the disk, it releases approximately 1044 joules of energy. Most of that energy is carried away by neutrinos, but a substantial fraction goes into the surrounding gas, heating it, compressing it, and if enough supernovae occur in a small enough region over a short enough time, driving it upward off the surface of the disk in a hot, fast-moving fountain of plasma. This is not a rare or unusual process. It is happening continuously, everywhere along the disk's spiral arms, wherever massive stars are forming and dying. The Orion Molecular Cloud, a star-forming region visible to the naked eye on a dark night, has been driving material upward into the halo for millions of years. The central molecular zone sends continuous outflows upward and downward toward the galactic poles. The combined effect of all this stellar feedback, integrated over the entire disk, is a persistent rain of gas rising from the disk into the lower halo, cooling as it rises, eventually stalling, condensing into clouds, and raining back down onto the disk over timescales of several 100 million years. This cycling material, this galactic breathing, is one of the primary mechanisms by which the Milky Way regulates its own star formation. Too much star formation produces too many supernovae, which drive too much gas out of the disk, which starves subsequent generations of star formation until the fountain gas rains back down and replenishes the supply. The galaxy is self-regulating through its own outflows, and those outflows happen directly above and below us, in the halo invisibly, continuously, and on a scale that dwarfs anything the human species has ever built or imagined. The Fermi and Erecita bubbles are, in this context, not anomalies. They are extreme expressions of a process that is normal. They are what the galactic fountain looks like when the central engine goes into overdrive, and their persistence in the halo, still visible, still expanding 2 to 4 million years after the event that created them, tells us something crucial about the halo itself. It is not an inert background medium. It is a dynamic, responsive, long-memory environment that records the galaxy's history in its temperature, its density, and its structure, preserving information about past events that the disk has long since forgotten. Above and below the Milky Way, the sky is a fossil record of explosions, and we are only just learning to read it. In 2022, a team of astronomers led by Jiwon Jesse Han at the Harvard-Smithsonian Center for Astrophysics published a result that, to my mind, represents one of the most elegant pieces of forensic astronomy in the last 20 years. Using data from the Gaia Space Telescope and a catalogue of a particular class of pulsating stars called K-giant stars, Han and colleagues mapped the three-dimensional shape of the Milky Way's stellar halo with a precision that had never previously been achievable. What they found was this: the stellar halo is not a sphere. It is not even a roughly spherical structure with minor perturbations. It is shaped, in the words of the paper, like a zeppelin, an elongated football-like ellipsoid, and it is tilted, not aligned with the disk, not symmetrical about the galactic plane. The stellar halo leans, offset by approximately 20 to 25 degrees from the axis of the galactic disk, stretched out in a direction that cuts diagonally across the plane of the galaxy, rather than rising straight above and falling straight below it. This is a deeply strange result, and the reason it matters enormously is what the tilt reveals about the past. The stellar halo is not, in any simple sense, the galaxy's natural equilibrium state. It is primarily the wreckage of collisions. Most of the stars in the stellar halo did not form inside the Milky Way's progenitor structure. They were torn from smaller galaxies that fell into the growing Milky Way over the past 10 to 12 billion years, their orbits disrupted by the tidal forces of the larger galaxy, their stars scattered into the diffuse high-velocity orbits characteristic of halo stars. The stellar halo is a graveyard of absorbed galaxies, and its shape records the geometry and trajectories of the most significant of those ancient collisions. The dominant structure in the inner stellar halo, and the event that most powerfully shaped the halo's current geometry, is called the Gaia-Enceladus merger, also known colloquially as the Gaia sausage. The story of how this event was discovered is one of the genuinely great recent chapters in observational astronomy, and it will serve as the human anchor of this story in its full depth when we get to that chapter. But let us establish the basic structure here. Approximately 8 to 10 billion years ago, the young Milky Way was not yet the orderly, settled spiral we know today. It was still actively growing, still absorbing the surrounding material of the local universe, and still susceptible to violent gravitational encounters with other galaxies of comparable mass. Into this growing Milky Way fell a dwarf galaxy, substantial, with a total mass in stars, gas and dark matter exceeding 10 billion solar masses. on an orbit that was not a gentle grazing encounter but a nearly head-on, deeply penetrating plunge directly into the Milky Way's heart. The collision did not end in a glancing blow. It ended in a total merger. The dwarf galaxy, which astronomers now call Gaia Enceladus, named for the Greek giant and the spacecraft that revealed it, was disrupted and absorbed over the course of perhaps 1 to 2 billion years. Its stars scattered into the inner halo of the Milky Way in highly radial, needle-like orbits that carry them deep into the galaxy and back out again to large distances. When Vasily Belokharov at the University of Cambridge and his collaborators plotted the velocities of these halo stars in 2018 using Gaia data, the distribution was striking. The stars traced out a sausage-like shape in velocity space, the signature of a population on radial, highly eccentric orbits, exactly what you would expect from the disrupted remnant of a galaxy that had fallen in on a nearly direct trajectory and been torn apart by the collision. The Gaia Enceladus merger is now understood to have been the defining collision in the Milky Way's history. The event that shaped the inner halo contributed at least 8 large globular clusters to the galaxy's halo population and likely puffed up or significantly disturbed the early disk of the Milky Way in ways that created the conditions from which the thick disk subsequently grew. It is, in the most literal sense, part of what we are made of. The heavy elements forged in the stars of the Gaia Enceladus galaxy are distributed throughout the halo that surrounds us today. Some of them, incorporated into molecular clouds that subsequently collapsed to form the Sun's stellar generation, may be inside your body right now. The tilt of the stellar halo, that 20 to 25 degree lean that Hahn and colleagues measured in 2022, is the frozen imprint of the Gaia Enceladus collision's geometry. Because the merger was not perfectly head-on, it imparted a net angular momentum to the debris that was distributed into the halo, and that angular momentum has been slowly precessing under the influence of the galaxy's potential ever since, winding itself into the elongated, tilted structure we observe today. The halo does not lean randomly. It leans in the direction that the last great collision pushed it, 10 billion years ago, and the lean preserves information about the angle and trajectory of that ancient impact that no other structure in the galaxy has retained. The further implication, and this is where the dark matter story re-enters the narrative with full force, is that if the stellar halo is tilted, the dark matter halo is probably tilted too. Dark matter and stars did not fall into the Milky Way separately. They came in together. The dark matter component of the Gaia Enceladus system merged with the dark matter halo of the young Milky Way, and the resulting combined dark matter structure should bear the geometric imprint of that merger, just as the stellar halo does. Several follow-up studies published in 2023 and 2024 have proposed that the Milky Way's dark matter halo is indeed oblate and tilted, with the long axis of the dark matter ellipsoid potentially aligned with the long axis of the stellar halo, which is to say, not aligned with the disk, not aligned with the galactic pole, but angled diagonally through the galaxy like a skeleton that doesn't quite fit the body it supports. The implications of a tilted dark matter halo are significant and still being worked out. The gravitational potential of the galaxy, which determines the orbits of every star, every satellite galaxy, every globular cluster, and every infalling cloud of gas, would be subtly asymmetric in ways that depend on the precise degree and direction of the tilt. The satellite galaxies of the Milky Way, distributed in their peculiar planar arrangement around the galaxy, may owe part of their current positions to the tilt of the dark matter potential, rather than just to their own orbital dynamics. The Magellanic Clouds, the 2 dwarf galaxies currently in the process of being disrupted by the Milky Way's gravity, hanging in the southern sky as glowing satellites visible to the naked eye from the southern hemisphere, may be orbiting within a gravitational landscape whose true shape is subtly different from the one that current models assume. There is also, floating quietly in the background of all this discussion, a more radical possibility that several theorists have begun to take seriously. If the dark matter halo is tilted by 20-something degrees relative to the disk, and if that tilt is a robust and long-lived feature of the galaxy's structure, rather than a transient aftermath of the merger that has almost fully relaxed, then there should be measurable dynamical consequences in the disk itself. The disk should be precessing. The warp of the Milky Way's outer disk, the well-documented, visually obvious fact that the outer regions of the galactic plane are not flat, but bent upward on one side and downward on the other, like the brim of an old hat that has been sat on, might be partially or substantially driven by the gravitational torque of a misaligned dark matter halo. The warp is one of the longest-standing puzzles in Milky Way structure, and the tilted halo may be part of its explanation. Or it may not. The measurements are not yet precise enough to say definitively, but this is the character of the science above and below the Milky Way. Every answer opens a corridor of new questions. Every measurement reveals something unexpected, and the uncomfortable, exhilarating truth is that the space directly surrounding our galaxy is simultaneously the most accessible region of the universe for detailed study, and the most stubbornly resistant to complete understanding. We live at the bottom of a vast and layered structure. We are just beginning to read the walls. The spring of 2018, a young astronomers meeting at the Max Planck Institute in Heidelberg hosted a graduate student named Gyu-Chul Meong, then working at the University of Cambridge under the supervision of Vasily Belokharov. Meong stood up in front of his peers and described a pattern he had found in data from the European Space Agency's Gaia satellite. Data released just months earlier in the second major Gaia data release, containing the positions, distances, proper motions, and line-of-sight velocities of more than 1.3 billion stars scattered across the entire sky. The pattern was a sausage shape in velocity space, a tight concentration of stars whose trajectories, when plotted in the three-dimensional space of stellar velocities, velocity toward the galactic center versus velocity perpendicular to the disk, formed an elongated, football-like distribution that should not have been there if the halo was simply a random scatter of stars on diverse orbits. The sausage shape was the signature of a specific kind of disrupted galaxy, one that had fallen in on a radial, nearly head-on trajectory, been torn apart, and scattered its stars into long, thin, needle-like orbits that plunged toward the galactic center and then slingshot back out to large distances. It was, Meong and colleagues proposed, the velocity fingerprint of the most significant merger in the Milky Way's history. To understand why the discovery of the Gaia-Enceladus merger is the deepest human story embedded in this documentary's subject, we need to back up much further, not to 2018, but to the 1970s and to a woman working at the Carnegie Institution of Washington, who was trying to understand why galaxies weren't flying apart. Vera Rubin was born in Philadelphia in 1928, and her path into astronomy was one that the institutions of science tried, at nearly every turn, to close. Princeton University refused to send her their astronomy PhD program information because women were not admitted. When she applied to Caltech to visit, she was told the institution did not accept female visitors to the astronomy facilities. When she presented her doctoral thesis research at an American Astronomical Society meeting in the early 1950s, her supervisor presented it on her behalf because she had recently given birth and could not travel. The hostility was not always dramatic. Sometimes it was simply the casual exclusion of a world that had decided, in advance and without evidence, that women did not belong at the frontier of physics. Rubin worked anyway. She worked with a methodical, almost mechanical patience, observing galaxy after galaxy, building rotational curves, measurements of how fast stars and gas clouds at different distances from a galaxy's center move in their orbits. The physics was settled. Everyone knew what a rotational curve should look like. According to Newtonian gravity, stars in the outer reaches of a galaxy should orbit more slowly than stars closer to the center, just as the outer planets of the solar system orbit more slowly than the inner ones. The mass is concentrated at the center. The further out you are, the weaker the gravitational pull, and therefore the slower the orbit. This was called Keplerian rotation, and it was as firmly established as any result in classical mechanics. Rubin found the opposite. Working with Kent Ford and their Carnegie colleagues through the 1970s and into the 1980s, measuring dozens of spiral galaxies with an image tube spectrograph, sensitive enough to record the spectral lines of gas clouds in the outermost reaches of galactic disks, Rubin and Ford found systematically flat rotation curves. The orbital velocities of stars and gas at the outer edges of galaxies did not decrease with distance from the centre. They stayed constant or even increased slightly, out to the very limits of detection. Galaxy after galaxy showed the same pattern. The outer stars were orbiting faster than they had any right to orbit given the visible mass of the galaxy. The only possible explanation, the explanation that had in fact been proposed independently by the Swiss astronomer Fritz Zwicky in the 1930s, when he noticed that galaxy clusters contained far too much gravity for their visible stars, which had not been taken seriously by the mainstream, was that there was additional invisible mass, a vast halo of matter surrounding and extending well beyond the visible disk of every galaxy, contributing gravitational pull without emitting any detectable light-dark matter. Rubin's rotation curves were the clearest and most systematic evidence that has ever been accumulated for the existence of dark matter in individual galaxies. They were the observational bedrock on which all subsequent dark matter physics has been built, and Rubin herself, reflecting on the work in later interviews, was characteristically precise about what she had found. Not an anomaly, not an outlier, not a case study, but a universal feature of spiral galaxies that told a story about what the universe is actually made of. Rubin never received the Nobel Prize in Physics, despite being nominated and widely considered a primary candidate for decades. She died in December 2016, still awaiting an honour that the Nobel Committee, which does not make posthumous awards, can no longer grant. I want to be direct about what I think of that fact. It is one of the clearest examples in modern science of an institution failing to recognise the magnitude of a discovery because of assumptions about who discoveries are supposed to come from. Rubin's rotation curves are not a minor contribution to galactic astronomy. They are foundational. They are the reason we know that 90% of the mass of the Milky Way lives above and below and around its visible disk in a form we cannot see. Every word of this documentary rests, in part, on work that she did while fighting an institutional headwind that most of her male colleagues never had to face. The dark matter halo that Rubin's work demanded, the invisible skeleton that now defines what we mean when we talk about what exists above and below the Milky Way, was a theoretical implication of her data long before it was accepted doctrine. In the 1970s, when she first presented the flat rotation curves, many astronomers were skeptical. The preferred explanation of many was not dark matter but modified gravity, a revision to Newton's laws at large scales that could produce flat rotation curves without requiring any new form of matter. This debate was not trivially resolved. It required decades of accumulating evidence from gravitational lensing, from the structure of the cosmic microwave background, from the behaviour of galaxy clusters colliding with each other. The bullet cluster collision, first analysed in 2006, being perhaps the single most decisive image showing that the mass of colliding galaxy clusters is separated from their hot gas, in a way that only makes sense if there is dark, collisionless matter present, before the scientific consensus settled firmly behind dark matter as the explanation. But even now, in 2025, we do not know what dark matter actually is. The most theoretically motivated candidate for the past several decades has been the WIMP, the weakly interacting massive particle, a hypothetical particle with a mass somewhere between 10 and 10,000 times the mass of a proton, interacting with ordinary matter only through gravity and the weak nuclear force. WIMPs emerged naturally from supersymmetric extensions of the standard model of particle physics, and their predicted abundance in the early universe matched, with almost suspicious precision, the abundance of dark matter inferred from cosmological observations. This coincidence that the same kind of particle required to fix the failings of the standard model of particle physics also produced exactly the right amount of dark matter was called the WIMP miracle, and it drove decades of experimental effort to detect them. Underground laboratories on every continent built tanks of liquid xenon and germanium crystals and searched for the signature of a WIMP colliding with an atomic nucleus, an event so rare that even a large detector containing tons of target material might see only a handful per year if WIMPs exist at the expected density. The Lux Zeppelin experiment in the Homestake mine in South Dakota, 1.5 kilometers underground to shield it from cosmic ray background, has searched for WIMPs with extraordinary sensitivity. As of April 2025, after 417 live days of data collection, LZ found no sign of WIMPs across a mass range from 3 GeV cell-acquired upward. No signal, no events above background expectation. The search is not over. The theoretical parameter space is not exhausted. But the region of WIMP mass and interaction strength that theorists most confidently predicted as the target has now been excluded. Either WIMPs exist in a part of parameter space that requires much larger, more sensitive experiments to reach, or WIMPs are not the answer at all. The dark matter halo that surrounds the Milky Way above and below, stretching to nearly 1 million light-years in every direction, containing 90% of the galaxy's total gravitational mass, may be made of something we have not yet conceptualized, let alone detected. I will admit honestly that I find this one of the most intellectually vertiginous situations in modern science. We live inside a structure whose dominant constituent is unknown, not vaguely unknown. Specifically, precisely, definitely unknown. We can map its gravitational influence. We can trace its shape through the orbits of stars and galaxies. We can weigh it, approximately, and we can describe its distribution. But we cannot say what it is made of. We cannot build a detector that catches it. We cannot produce it in a laboratory. We are surrounded, above and below and in every direction, by something that constitutes 90% of the mass of our home galaxy, and is, in the most fundamental sense, a complete mystery. Vera Rubin spent her career measuring a gravitational phenomenon whose physical cause remains unresolved 5 decades later. She found the bones of the galaxy. Identifying what the bones are made of is the work of the generation that followed her, and the generation after that, and possibly several more generations beyond them. The bones are there. We can feel them, we just cannot see them. And if Rubin's work established the invisible skeleton, then a new generation of astronomers, working with instruments she never had access to, from the Gaia satellite to Erecita to the forthcoming Vera Rubin Observatory, named in her honour and scheduled to begin its first full-sky survey, are now trying to read what is written on those bones, not just the fact of their existence but their history. What fell in to build them, when, from what direction, and at what cost to the galaxy that absorbed the impact. That history is written in the stellar streams above and below the galactic disk, and it is stranger, older, and more violent than anyone expected. If you could somehow stand outside the Milky Way and look at it from a distance of, say, 2 million light-years, far enough to see the entire structure from stellar disk to the edges of the dark matter halo, what you would see would not be a clean, crisp galaxy with a well-defined boundary and empty space beyond. You would see a system wrapped in ghosts, spreading above and below the galactic disk, threading through the stellar halo in great looping arcs. Wound around the visible galaxy in multiple layers and orientations are the remnants of dozens of smaller galaxies that the Milky Way has consumed over the course of its 10 billion year history. These are not figurative ghosts. They are literal, coherent streams of stars, hundreds of thousands of them, still tracing the orbital paths of the galaxies from which they were torn, their positions and velocities, preserving the trajectories of their progenitors like grooves, pressed into the halo by the ghost of a record needle. Each stream is a forensic record of a gravitational crime that the galaxy committed billions of years ago and has never fully erased. The most spectacular of these is the Sagittarius stream. The Sagittarius dwarf galaxy is a small, diffuse satellite galaxy currently in the final stages of being destroyed by the Milky Way's tidal forces. It sits roughly 70,000 light-years from the Sun, actually closer than the centre of the Milky Way, and it has been orbiting the galaxy and being slowly consumed for several billion years. Each time it passes close to the galactic disk, the Milky Way's gravity strips away a portion of its stars and scatters them into tidal streams that wrap in great arcs around the entire galaxy. The Sagittarius stream is now known to wrap almost completely around the Milky Way, tracing loops above and below the galactic plane in a sinuous helix whose full extent reaches 200,000 light-years from the galactic centre. In 2002, Vasily Belokharov and collaborators used data from the Sloan Digital Sky Survey to trace the Sagittarius stream across a significant portion of the sky, and the result was extraordinary. A river of stars undiluted enough by the background population to be traced as a coherent structure over tens of thousands of light-years, looping above and below the galactic plane in multiple wraps that record successive passages of the Sagittarius core through the Milky Way's tidal field. Each wrap is slightly different distance, slightly different stellar population, reflecting the gradual decay of the dwarf galaxy's orbit over billions of years as tidal stripping robs it of mass and energy. The Sagittarius stream is the most prominent of its kind, but it is far from the only one. By 2025, following data releases from the Gaia satellite, astronomers had identified dozens of stellar streams in the halo of the Milky Way, each one the archaeological remnant of a galaxy or globular cluster that the Milky Way absorbed at some point in its history. The GD1 stream, stretching across 100 degrees of sky, the Orphan stream, whose progenitor has not yet been definitively identified, the Styx stream, the Hylas stream, the Silga stream, each one a name attached to a river of stars flowing above and below the galactic plane through the halo, each one a chapter in the violence of the Milky Way's growth. Collectively, these streams represent a radical transformation in how astronomers think about what the space above and below the galaxy actually contains. For most of the 20th century, the halo was thought of as a static ancient background population. Old stars scattered more or less uniformly in a roughly spherical distribution, remnants of the galaxy's earliest formation epoch, placed in their current positions billions of years ago, and slowly drifting in their orbits ever since. The streams destroyed that picture. The halo is not static. It is not ancient and undisturbed. It is a dynamically active environment in which new material is continuously being deposited from disrupted satellites, the streams gradually spreading and dispersing into the background over billions of years, but leaving coherent, traceable structures for hundreds of millions to billions of years after the disruption event. The streams also serve as extraordinarily sensitive gravitational probes, and this is where their scientific importance becomes more than archaeological. A stellar stream is, in effect, a continuous chain of test particles tracing orbits in the Milky Way's gravitational potential. Any perturbation to that potential, a concentrated clump of dark matter passing through the stream, a satellite galaxy approaching on a close orbit, even the misalignment of the dark matter halo, will leave a measurable imprint on the stream's structure, gaps, density variations, kinematic perturbations, changes in width. By modelling the predicted shape of a stream in a smooth gravitational potential, and then comparing that model to the observed stream, astronomers can detect and characterise gravitational perturbations that would otherwise leave no observable trace. This technique, using stellar streams as gravitational seismographs, has produced some of the most exciting recent results in the search for dark matter structure. In 2023, analysis of the GD1 stream, using data from Gaia and spectroscopic follow-up, suggested the presence of a gap in the stream consistent with a gravitational encounter with a dark matter subhalo, a smaller concentration of dark matter within the larger halo with a mass of perhaps 10 million solar masses, containing few or no stars and therefore entirely invisible to optical telescopes. If confirmed, This would be the first direct detection of a dark matter substructure within the Milky Way's halo, a clump of pure dark matter orbiting above and below the galactic disk, betrayed only by the gravitational footprint it left on a river of stars. The detection is not yet certain, the statistics are not yet definitive, but the possibility exists. In the stellar streams threading the halo above and below us, the dark matter substructure predicted by lambda CDM cosmology may be quietly leaving its fingerprints, waiting for data precise enough to read them. But there is another structure in the space above and below the Milky Way that raises questions of a different and more fundamental kind. Questions that do not merely probe the galaxy's history or the nature of dark matter, but that challenge the standard cosmological framework itself. This is the problem of the plane of satellite galaxies. The Milky Way has, as of the most recent comprehensive census, somewhere between 40 and 50 known satellite galaxies, small, gravitationally bound systems orbiting within the dark matter halo, ranging from the large and small Magellanic Clouds, which are substantial enough to be visible to the naked eye from the southern hemisphere, down to tiny ultra-faint dwarf galaxies, containing as few as a few thousand stars, discovered only through the deep photometric surveys of the last decade. In the standard cosmological model, lambda CDM, these satellite galaxies should be distributed roughly randomly around the parent galaxy, scattered in all directions above, below, and within the plane of the disk. The model predicts that small galaxies fall into a larger galaxy's dark matter halo from all directions because the cosmic web delivers material from every direction rather than preferentially from any single plane. What is actually observed is dramatically different. The satellite galaxies of the Milky Way are not randomly distributed. They are preferentially arranged in a thin, rotating plane, known in the technical literature as the vast polar structure, VPOS, oriented roughly perpendicular to the Milky Way's disk, tilted steeply above and below the galactic plane. Approximately half of the known satellites lie within this thin planar structure, orbiting in a coordinated fashion that is statistically wildly improbable if they arrived from random directions. The probability of this arrangement occurring by chance in a lambda CDM universe has been estimated at less than 1% by some analyses, and substantially lower by others. The plane of satellite galaxies is, to put it plainly, a problem for the standard model. Not a fatal problem, there are proposed explanations involving cosmic filament infall, the breakup of a larger satellite system, or observational biases in our ability to detect faint satellites at different galactic latitudes. But a problem that has persisted and deepened as more satellites have been discovered, and that the standard model has not yet convincingly resolved. It joins a small but growing list of challenges to lambda CDM at small scales. The missing satellites problem. The model predicts many more satellite galaxies than are observed. The too big to fail problem. The model's most massive predicted subhalos should contain visible galaxies but do not. As evidence that something in our picture of the small-scale behaviour of dark matter may be incomplete, the satellites that do exist in this planar structure, above and below the Milky Way, are themselves conducting a cosmic drama that is already partly played out, and will eventually transform the entire local galactic environment. The Large Magellanic Cloud, currently orbiting approximately 163,000 light-years from the galactic centre, is not a stable, long-term resident of the Milky Way system. It is almost certainly on its first close approach, arriving recently in cosmological terms, carrying with it not just stars, but a massive trailing cloud of gas, called the Magellanic Stream that arcs across nearly 200 degrees of the southern sky. The Magellanic Stream is a river of neutral hydrogen gas stretching from the Large Magellanic Cloud back through its orbital path, slowly raining down onto the Milky Way's disk and adding fresh, relatively metal-poor fuel to the galaxy's star formation reservoir. And the Large Magellanic Cloud is, according to a 2019 study by Marius Kortun and collaborators, on a collision course. The estimates vary. The uncertainty in the LMC's precise orbit and mass makes the timescale hard to pin down exactly. but the central estimate is that the Large Magellanic Cloud will merge with the Milky Way in approximately 4 billion years, give or take roughly 1.2 billion years. When it does, the consequences will be extraordinary. The simulations suggest that the LMC merger will dramatically disturb the outer halo, triggering a new wave of star formation, delivering significant new mass to the galactic disk, and most dramatically, potentially waking up Sagittarius A, the currently dormant supermassive black hole at the galactic center. The LMC contains a large reservoir of gas. When it is disrupted, that gas will rain down on the galactic center region over the course of hundreds of millions of years, and some of it will find its way to the accretion disk of Sagittarius A, the black hole, currently consuming matter at a rate so low that its X-ray luminosity is barely measurable, could reignite. It could become, temporarily, an active galactic nucleus. It could inflate new Fermi bubbles. It could drive new X-ray outflows into the halo. The scars left by past eruptions above and below the disk, the structures that Erosita revealed in 2020, could be replicated, amplified, and renewed. 2 billion years from now, the galaxy that exists above and below the Milky Way will be a different structure than the one we inhabit today. The halo will have been stirred. The satellite configuration will have been transformed. The black hole at the center will, probably, be awake. We live in a quiet period between eruptions, between mergers, a brief astronomical interlude in which the galaxy has settled enough to allow suns like ours to shine steadily for billions of years, long enough for life to evolve, look upward, and begin to ask what is actually up there. The answer, it turns out, is anything but quiet. In January 2020, a team of astronomers led by João Alves at the University of Vienna, working with Harvard's Alyssa Goodman, Catherine Zucker, and Douglas Finkbeiner, published a discovery that transformed the understanding of the Milky Way's local structure in a way that no one had expected. They called it the Radcliffe Wave. The Radcliffe Wave is a coherent, undulating filament of star-forming gas, stretching approximately 9.0 light-years along the local arm of the Milky Way, the spiral arm in which our solar system resides, with a wave-like shape that crests about 500 light-years above and dips about 500 light-years below the midplane of the galactic disk. It is the largest coherent gas structure ever identified in the Milky Way, 400 light-years wide, containing many of the nearby molecular clouds and stellar nurseries that astronomers had been studying individually for over a century, without realizing they were part of a single, enormous, oscillating structure. Orion is part of it, Perseus is part of it, Taurus and Ophiuchus, the great star-forming regions visible in the winter and summer skies, are part of it. The solar system is currently about 500 light-years from the nearest crest of the wave. On the inside, closer to the galactic center, approximately 13 million years ago, our Sun was embedded within the wave, passing through a densely concentrated stretch of molecular cloud material near the Orion region that was, at the time, undergoing intense star formation and producing a series of supernova explosions from its most massive stellar offspring. The passage through that region left traces in the geological record of Earth. Elevated rates of cosmic ray bombardment, enhanced deposition of radioactive isotopes in deep-sea sediments, and created the local bubble, the roughly 1,000 light-year-wide cavity of hot, low-density gas in which our solar system currently resides, carved out by perhaps 15 to 20 supernovae that detonated within the last 10 to 20 million years. In approximately 13 million years, the solar system will cross the Radcliffe Wave again. The Radcliffe Wave's existence, its remarkable length, its coherence over 9,000 light-years, and its oscillating shape, presented astronomers with an immediate puzzle. What makes a 9,000 light-year structure undulate? The wavelength and amplitude of the oscillation are consistent with a gravitational perturbation, something impacting the disk from above or below and sending a wave propagating through the disk's gas layer. The most recent and detailed analysis, published in Nature Astronomy in 2024, used stellar kinematics from Gaia to demonstrate that the wave is not static but is genuinely moving. oscillating upward and downward through the disk plane as a coherent wave, like the ripple spreading across a still pond after a stone is dropped into it. The stone in this case may have been a galaxy. We know the Milky Way disk has been impacted from above relatively recently, on astronomical timescales. The Sagittarius dwarf galaxy has been passing through the disk multiple times over the past few billion years, each passage depositing orbital energy into the disk's gas and stellar populations in a way that has been suggested in a 2021 paper by Teresa Antoja and collaborators as the driver of the phase-space spiral observed in Gaia data. A spiral pattern in the distribution of stellar positions and velocities above and below the midplane that is the unmistakable dynamical signature of a disk that has perturbed from outside and has not yet fully settled back into equilibrium. The Gaia phase-space spiral, sometimes called the Gaia snail because of its shell-like appearance in the phase-space diagram, was reported in 2018 using the second Gaia data release, and it is one of the most visually arresting diagrams in all of modern astronomy. Take the vertical position of stars in the disk and plot it against their vertical velocity, and instead of a smooth, symmetric distribution as you would expect from a settled, undisturbed disk, you see a spiral, a galaxy-scale snail shell, wound not in physical space but in the abstract mathematical space of positions and velocities, recording the lingering dynamical memory of a gravitational impact that the disk has not yet forgotten. The timescale of the spiral's winding corresponds to a perturbation event roughly 500 million to 1 billion years ago, broadly consistent with one of the more recent passages of the Sagittarius dwarf galaxy through the disk. The galaxy reached down from above briefly and pulled, and the disk is still ringing from that pull today, its stars still sloshing above and below the midplane in a slowly unwinding gravitational echo, visible only because we have an instrument precise enough to read it. This, the Gaia snail, represents one of my favourite examples of what modern astronomical data can actually achieve, and I want to dwell on it for a moment, because it illustrates something profound about the relationship between the space above and below the Milky Way and the disk we live in. The disk is not isolated from what lies above and below it. It does not float in the halo undisturbed, following its own dynamics without reference to what surrounds it. The halo is in constant gravitational dialogue with the disk. Satellite galaxies fall through the disk from above and below. Streams of gas rain down from the circumgalactic medium. The gravitational potential of the dark matter halo, tilted, complex, shaped by ancient mergers, pulls the disk's warp into its current configuration, and every one of these interactions leaves traces in the stellar kinematics of the disk that are still visible billions of years after the event. The disk remembers what happened in the halo remembers what fell into it from outside. And with an instrument like Gaia, which has measured the positions, distances, and three-dimensional velocities of more than 5 billion stars with an accuracy approaching the width of a coin, seen from 10,000 kilometers, we now have the capacity to read those memories in unprecedented detail. But there is one more structure above and below the Milky Way that I have not yet described, and it may be the most important of all because it is the one whose existence determines whether the galaxy continues to form stars at its current rate or gradually exhausts itself over the coming billions of years and fades. It is the infall of gas from outside. The Milky Way is consuming the gas in its disk by forming stars. At its current star formation rate, roughly 2 to 3 solar masses per year, it would exhaust its current cold gas reservoir in approximately 2 billion years. But the disk has been forming stars at roughly this rate for 8 to 10 billion years and has not yet run dry. The only way this is possible is if the galaxy has been continuously replenished with fresh gas from an external source, and the likely source is the circumgalactic medium and the larger cosmic environment beyond it. High-velocity clouds are the most visible tracer of this infall process. These are clouds of neutral hydrogen gas moving at velocities inconsistent with the rotation of the galactic disk. Hundreds of kilometers per second, faster or slower than the disk material at the same location, and raining down onto the Milky Way from above and below. First discovered in 1963 by Gail Smith at the Dwingelu Radio Telescope in the Netherlands, who noticed anomalous velocity features in 21 centimeter hydrogen emission that had no obvious explanation in terms of the normal disk rotation. High-velocity clouds have been studied for 6 decades without the fundamental question of their origin being definitively answered. Some are clearly associated with the Magellanic Stream, stripped gas from the large and small Magellanic Clouds raining onto the Milky Way as those galaxies are tidally disrupted. Some appear to be condensations of the cooling circumgalactic medium, gas that has cooled from millions of Kelvin to a few thousand Kelvin and formed a neutral cloud that is now falling under gravity toward the disk. A 2024 simulation study using the Illustris TNG50 cosmological simulation, which models Milky Way-like galaxies with sufficient resolution to study CGM structure, found that in simulated galaxies resembling the Milky Way, only about 17% of high-velocity cloud analogues could be straightforwardly attributed to a single clear origin, confirming observationally what many had suspected, that the high-velocity cloud population is a heterogeneous mixture of different physical processes, all converging on the same observational signature from different distances and different physical locations above and below the disk. This heterogeneity is, in a way, the most honest summary of what the space above and below the Milky Way actually is. It is not a single thing, it is not a single layer, it is a superimposed, interconnected, dynamically coupled collection of structures and processes operating simultaneously at different scales, different temperatures, different distances, and different timescales. There are the Fermi and Erosita bubbles roaring outward from the galactic center at 3 million kilometers per hour. There is the stellar halo, ancient and sparse, shaped by mergers that ended 10 billion years ago. There is the circumgalactic medium, breathing in and out with the rhythm of star formation. There is the dark matter halo, vast and invisible, tilted at a diagonal to everything we can see, providing the gravitational framework within which all of the above exists. There are tidal streams recording the orbital paths of galaxies the Milky Way consumed millennia ago. There are satellite galaxies orbiting in a plane that should not exist. There are high-velocity clouds raining inward from every direction, carrying gas that will fuel the next generation of stars. And underneath all of it, in the plane of the disk itself is still ringing, still moving upward and downward in the slow gravitational oscillation of the Gaia snail, still carrying the memory of impacts from above and below that it has not yet forgotten. The space above and below the Milky Way is the galaxy's history, written in gas and stars and invisible matter, covering a volume 100 times larger than the visible disk, and containing almost none of the light. It is the largest library in the local universe, and until very recently we did not even know it existed. The story of what exists above and below the Milky Way is not finished. It is barely begun. When I look at the trajectory of this field from the mid-20th century to the present, what I see is an accelerating pace of discovery, driven not by theoretical breakthroughs, though there have been those, but by instrument. The pattern is consistent and humbling. We do not know what is up there until we build something capable of seeing it. And the history of the last 3 decades is a history of instruments, revealing that the space above and below the galaxy is far more populated, far more structured, and far more dynamic than the generation before had any reason to suspect. Gaia changed everything. The European Space Agency satellite, launched in December 2013 and still operating as of this writing, has delivered a dataset of breathtaking precision. Positions accurate to 20 microarcseconds, parallax distances good to 10% out to tens of thousands of light years, proper motions that allow astronomers to reconstruct the 3-dimensional trajectories of billions of individual stars. Before Gaia, the stellar halo was known to be roughly spherical and populated by old metal poor stars. After Gaia, it is a geological record of successive mergers, a tilted ellipsoid shaped by a single catastrophic collision 10 billion years ago, threaded with dozens of identifiable tidal streams and still dynamically active in ways that challenge the assumption of equilibrium that underpinned most prior modelling. Gaia did not just improve the precision of existing measurements, it revealed an entirely different picture of the galaxy. Rosita transformed the circumgalactic medium. The discovery of the Rosita bubbles in 2020 was the headline result of its first all-sky survey, but the deeper legacy of Rosita is the comprehensive mapping of the warm-hot CGM that the telescope enables. The 2024 analysis by Nicola Locatelli and colleagues of the warm-hot CGM in the temperature range, around 1 million Kelvin, found structure, temperature gradients, and density variations that can now be compared to cosmological simulations in unprecedented detail, testing models of galaxy evolution and gas cycling that had previously been constrained only by simulations. The CGM is no longer a theoretical construct. It is an observed environment with measurable properties, and Rosita is still accumulating data. The forthcoming Vera Rubin Observatory, the Large Synoptic Survey Telescope, renamed in 2019 in honor of the woman who found the galaxy's dark skeleton, will begin its full legacy survey of space and time in the next few years, imaging the entire accessible sky every 3 nights to a depth that will transform our census of the faint stellar populations of the Milky Way's halo. The RR Lyrae survey that Rubin Observatory will conduct is expected to extend the known traced volume of the stellar halo by an order of magnitude, pushing the detectable boundary of Milky Way stars from the current outer limit of roughly 1 million light-years to distances approaching the estimated edge of the dark matter halo itself. If there are stellar structures, streams, clouds, disrupted satellites in the outer halo that are currently invisible because they are too faint for existing surveys, Rubin Observatory will find them. The Roman Space Telescope, NASA's Wide Field Infrared Survey facility currently in development, will extend the search for halo substructure into the infrared, cutting through the dust obscuration that limits optical surveys in directions close to the galactic plane and enabling measurements of stellar chemistry and kinematics in the inner halo with Gaia-level precision over a much wider area. Roman will also conduct a deep survey of the galactic bulge region that will, among other things, refine estimates of the mass and kinematics of the central dark matter distribution, the innermost part of the dark matter halo, where the predictions of different dark matter models diverge most sharply. And on the particle physics side of the dark matter search, the next generation of experiments after LUX-ZEPPELIN, including XLZD, Sinon LZ Darwin, a proposed ton-scale noble liquid detector, with sensitivity extending well into previously unexplored WIMP parameter space, will either detect WIMPs at a level that has never before been accessible, or will exclude a further enormous region of the theoretical parameter space. There is a possibility, not a certainty, but a real and serious scientific possibility, that within the next decade the experiment will push into the neutrino floor the fundamental irreducible background produced by atmospheric and solar neutrinos, beyond which it becomes effectively impossible to search for WIMP IMS without distinguishing a WIMP signal from a neutrino background. If that boundary is reached without a detection, the WIMP hypothesis will not be dead, but it will be in serious trouble, and the theoretical community will face an increasingly urgent need to develop and test alternative dark matter candidates. The leading alternatives are not trivial or ad hoc. Axions, extremely light, weakly interacting particles originally proposed in the 1970s to solve an unrelated problem in quantum chromodynamics, are now considered by many theorists as at least as well motivated as WIMPs. The ADMX experiment at the University of Washington and several competing axion search experiments are currently exploring the axion mass range most favoured by cosmological constraints, and a detection of an axion signal would be one of the most consequential discoveries in the history of physics. Primordial black holes formed in the very early universe, before star formation began, potentially comprising some or all of the dark matter as a population of compact objects distributed through the halo remain viable in certain mass ranges not yet excluded by observations. What is clear is that the dark matter problem will not be solved by theoretical ingenuity alone. It will be solved by data. And the data is coming from instruments already operating and instruments under construction at a rate that makes the next decade of observational astrophysics one of the most exciting periods in the science's history. There is one more question hanging over this story that I want to address directly before we reach the close, because it is the question that connects the abstract science of halos and dark matter and bubbles to the most human possible dimension of the subject. The Milky Way is not permanent. The structures above and below the galactic disk, the halo, the circumgalactic medium, the dark matter distribution, the satellite galaxies, are not a stable eternal architecture. They are a snapshot, a single frame in a continuous process of galactic evolution that has been running for 10 billion years, and will continue for many billions more. The halo we observe today is not the halo that existed 5 billion years ago, and it will not be the halo that exists 5 billion years from now. We have discussed the coming merger with the Large Magellanic Cloud. But there is a larger question about the Andromeda Galaxy, M31, which sits 537 million light-years away and has been one of the central objects in discussions of the Milky Way's long-term future for decades. The canonical prediction derived from estimates of Andromeda's approach velocity and published in a landmark 2012 paper using Hubble Space Telescope measurements was that the two galaxies would undergo a major merger in approximately 4 to 5 billion years, gradually combining their stellar and dark matter halos into a giant elliptical galaxy, sometimes called Milkomeda or Milkdromeda. However, a 2025 paper published in Nature Astronomy by Till Sawala and collaborators, based on an analysis of 100,000 computer simulations of the local group's future dynamics, found something considerably more uncertain. The probability of a close collision between the Milky Way and Andromeda within the next 10 billion years is only approximately 50%. Not near certain, about even odds. The simulations, which incorporated the observational uncertainty in Andromeda's tangential velocity, a quantity that remains difficult to measure precisely, found that in a substantial fraction of possible future histories, the two galaxies have a glancing encounter or miss each other largely, continuing as separate galaxies for many billions of years beyond any timescale of immediate relevance. This is an extraordinary result, and ESA's Hubble Space Telescope confirmed the uncertainty in a 2025 press release that concluded, "There is approximately a 50-50 chance of no Milky Way-Andromeda merger during the next 10 billion years. Not a certainty, not even a high probability. The future of the Milky Way's halo, the fate of all that invisible architecture above and below us, hinges on a measurement uncertain by less than 10 kilometers per second in a galaxy 2.5 million light-years away. The universe's largest structures are determined by margins this thin. What is certain is that the story of what exists above and below the Milky Way is not yet close to being finished. The halo is dynamic. The CGM is cycling. The dark matter is structuring. The satellite galaxies are orbiting and infalling. The Fermi and Erecita bubbles are expanding. The stellar streams are dispersing. The phase-space spiral is unwinding. The Radcliffe wave is oscillating. The local bubble is slowly fading as the supernovae that carved it recede into the past. All of these processes are happening right now. Above you and below you, in a volume 1 million light-years across, the galaxy's most consequential dynamics are unfolding in silence and invisibility, in 100 million degrees of hot plasma and 1 trillion solar masses of dark matter that no instrument will ever directly touch. The next generation of observatories will read further into that volume than any human instrument has reached before. They will find structures that surprise us. They will raise questions that make our current open loops look simple. They will, in the tradition of every great observational advance in astronomy, reveal that the universe is larger, stranger, and more structured than we imagined when we built the tools that revealed it. That is not a disappointment, that is the promise. There is a moment in the career of almost every astronomer who has studied the halo of the Milky Way when the scale of the problem they are working on becomes personal. Not intellectually personal, in the way that any difficult problem eventually becomes your problem. Personally personal, in the way that you look up at the night sky and understand, in some non-verbal, pre-linguistic part of your cognition, that the darkness you are looking at is not empty, that the void between you and the next star is threaded with a structure of extraordinary complexity, most of it invisible, all of it shaped by a history spanning billions of years. You are not looking at nothing. You are looking at an archive. Vera Rubin had that moment standing at telescopes at Kitt Peak in Arizona, watching the spectra of galaxies scroll across her instruments night after night, finding the same flat rotation curves in galaxy after galaxy, understanding that the visible universe was a film floating inside something enormous and dark and gravitationally decisive. She had that moment decades before the instruments existed to map what she had inferred. She found the skeleton by feel through mathematics and patience, and a willingness to trust what the data said, even when the data said something that the textbooks did not accommodate. She spent the rest of her life in that understanding, surrounded by the invisible, charting what could not be directly seen. Mengsu had that moment staring at the gamma-ray all-sky map from the Fermi satellite, watching the foreground emission peel away under his statistical analysis, revealing two enormous lobes erupting symmetrically from the galactic centre, a structure too large, too well-defined, and too unexpected to be a statistical fluctuation, and too new to have an explanation ready-made. He published the discovery and spent years defending and refining it, while the astrophysics community spent years trying to explain it, and the explanation 15 years later is still not fully settled. João Alves had that moment looking at a 3D dust map assembled from 1 billion stars measured by Gaia, watching the molecular clouds of the Orion Arm arrange themselves not in the ring that astronomers had drawn for a century and a half, but in a wave, a 9,000 light-year oscillating filament that the solar system had passed through, star-forming region by star-forming region, for tens of millions of years without anyone realizing it was a single coherent structure. What all of these moments share is the experience of discovering that the familiar contains more than the familiar suggests. The night sky that human beings have gazed at from open fires and hilltops and ship decks and telescope domes for thousands of years is not a simple backdrop of light. It is the surface of a structure that extends 1 million light years above and below the place where we stand, most of it invisible, all of it active, shaped by violence and gravity and time on scales that no human life can contain. We are embedded in the middle of one of the universe's great galactic systems, at a particular moment in that system's long history, after the last great merger before the next one. We are in the quiet between catastrophes. The halo above us holds the memory of 10 billion years of collision and absorption, the stellar streams still flowing, the Gaia Enceladus debris still precessing in its tilted ellipsoid. The hot CGM above us holds the missing baryons of a cosmological accounting problem we spent decades not being able to solve. The Fermi and Erecita bubbles above and below us record an eruption from our galaxy's own black hole, whose cause we cannot yet name. And the dark matter, that specific, measured, gravitationally indispensable, physically unidentified presence stretching in all directions around us to a distance of nearly 1 million light-years, remains the most tantalizing open question in any discipline of science that I know. Not because it is vague, because it is precise. We know its mass to within a factor of 2. We know its distribution to the resolution of our best simulations. We know what it does in immense and quantified detail. We do not know what it is, a mass of approximately 1.3 trillion solar masses, arranged in a roughly oblate spheroid above and below and around a thin disk of stars and gas, and we cannot say what a single one of its constituent particles is made of, because no experiment on Earth has ever detected one, That is the condition we are in. That is where the science stands right now, in this particular moment, in this particular watch. I find it. I genuinely find it not frustrating but clarifying. The scale of what we do not know is not a failure of science. It is a measurement of how much further there is to go. Every great discovery in the story of what exists above and below the Milky Way has not been the end of a question, but the beginning of three more. Rubin's rotation curves demanded dark matter, and dark matter demands a particle physics explanation that we cannot yet give. The Fermi bubbles demanded an energy source, and the energy source demands a decision between two mechanisms we cannot yet distinguish. The Gaia-Enceladus merger explained the tilted halo, and the tilted halo demands a revised dynamical model that we cannot yet write with full confidence. The high-velocity clouds demanded an origin, and the origin refuses to be single or clean or easy. Every answer is a door. Every door opens into a larger room. And the rooms keep getting larger. The universe does not owe us a satisfying resolution. It does not arrange itself for our narrative convenience. The question of what actually exists above and below the Milky Way is not a question with an ending. It is a question with a horizon, and every advance in instrumentation pushes that horizon further, revealing more structure, more complexity, more history than was visible before. We are not approaching a final answer. We are approaching the next generation of better questions. There is a star called HE 04375439, an RR Lyrae type variable in the distant outer halo, sitting approximately 200,000 light-years above the galactic plane, so far from the disk that it takes the light, leaving it longer to reach us than the distance to the nearest other galaxies in the local group. This star formed almost certainly inside the Milky Way or one of its consumed satellites, and was thrown outward by some ancient gravitational interaction into an orbit that carries it through the remotest reaches of the halo. It is one of the most distant Milky Way stars ever identified, and it is alone out there, in that vast, dark, nearly empty volume, surrounded by the invisible dark matter halo that we cannot see, above a galaxy it can barely feel, circling around a gravitational centre that is, from its location, the faintest imaginable smear of light in a dark and indifferent sky. From where that star sits, the Milky Way, your galaxy, a galaxy that contains your sun and your planet and your entire civilization, looks like nothing. A diffuse, unresolved glow, a suggestion of brightness in one direction of the sky. Not a home, not even a shape, just a distant concentration of matter that happens to pull faintly at the star's velocity. And yet that star is still technically inside the Milky Way, still part of it, still gravitationally bound to the whole architecture we have been describing, the disk, the halo, the CGM, the dark matter. Still, in whatever sense the word applies to a single old star orbiting alone in the dark, one of us, there is something in that image that I return to more than most. We ask what exists above and below the Milky Way. We build instruments and calculate masses and trace streams and map temperatures and search for dark matter particles in tanks of liquid xenon underground. All of that is real and rigorous and important. But underneath all of it, in the same way that the dark matter underlies the visible structure of the galaxy, there is a simpler, stranger truth. What exists above and below the Milky Way is us, extended, distributed, ancient and invisible, and most of it unknown. We are not at the edge of the galaxy looking in. We are inside the galactic system looking out, from the middle of a structure that extends in every direction to distances that no human mind can truly hold. The halo is not above and below us, in the way that the sky is above and below a building. It is around us in every direction, continuous with the disk, continuous with the local bubble, continuous with the tidal streams and the CGM and the dark matter and the satellite galaxies. We are embedded in it. We have always been embedded in it. We just didn't know it was there. And the discovery that it is there, the slow, accumulating, multi-decade, multi-instrument revelation that the Milky Way is a far larger, far stranger, far more dynamic system than the textbook pinwheel we thought we knew, is, to my mind, one of the deepest and most consequential reorientations of the human understanding of our place in the universe that science has yet achieved. We thought we knew where we lived. It turns out the house is much bigger, and most of the rooms we still haven't opened.